In this session, we discuss process flow analysis. The main concept in process flow analysis is the Little's law. Perhaps no other formula in business school has an impact as high as the Little's law. When we look at a process, we see 5 elements: inputs, outputs, resources, information structure, and the network of activities and buffers. Flow units, in terms of inputs, come into the network of activities and buffers. They benefit from human and capital resources and information structure and become outputs. In this network, we have activities, rectangles, and buffers, triangles. Activities are value added, buffers are non-value added. We said enterprises compete with each other in a 4-dimensional space of time, cost, quality, and variety. Among them, it is believed that in today's competition, time plays the most important role, and it is believed that it can have profound impact on other 3 dimensions. For example, if flow time is short, then flow units spend less time in manufacturing and service settings. They have less time to absorb overhead costs, and when the flow time is low, that means non-value added part of the process is small. When flow time is short, quality is high, because one of the basics of flow time reduction is if quality is low, you should stop the process. And when you stop the process, flow time is not low. Indeed, nothing flows, so flow time cannot be short. When flow time is low, as we will later see based on the Little's law, inventory is low. When inventory is low, that means you don't have too much flow units in the processes. Therefore, if customers change their preferences, and if new technology comes into the market, you can quickly and easily switch to new products because you don't have too much work in process. So we understand enterprises compete with each other in a 4-dimensional space, and in that 4-dimensional space, time plays the most important role, and time can have profound impact on the other 3 dimensions. According to the Little's law, time is connected to flow rate and inventory. Flow time is the time required by a flow unit to move through all the processes from entering point to the exit point. Flow time is not the same for all flow units. Why? Because first, we may have different flow units. Patients who go to a physician office are entirely different flow units. One of them may stay with the physician for 2 minutes, the other may stay for 20 minutes. Second, even if 2 flow units are exactly the same, they may have different flow times because we are not living in a deterministic world. Things are probabilistic. Even if you are doing 2 exactly identical tasks, one of them may take 10 minutes, the other one may take 11 minutes. So we will not talk about flow time of a specific flow unit, but we talk about average flow time of all flow units. Then we have flow rate, the number of flow units passing a specific point, entrance point, exit point, any intermediate point per unit of time. Flow rate also is not constant. It changes over time. During an hour, sometimes we may have 1 customer per minute coming into a grocery store. Sometimes we may have 2 customers per minute. Sometimes we may have no customer per minute. And one other reason is seasonality. For example, more customers per hour come to a grocery store in the morning and in the afternoon compared to the other times. Regarding the flow rate, also we don't talk about flow rate in each specific time unit, but we talk about average flow rate per time unit, which is constant in a stable process, and we refer to average flow rate as throughput. And then we have inventory. When we go to a car assembly plant, we see a lot of work in process over there. That is inventory. When we go to a physician office, we see patients in the waiting room. That's inventory. The number of flow units in inventory of an assembly plant may vary from one day to the other day. The number of patients waiting in the waiting room of a physician may vary from one day to the other day, or from 1 hour to another hour. We talk about the average inventory. We look at all days and all hours, average them, that would be the average inventory. We talk about average inventory, average flow rate, which is throughput, and average flow time. According to the Little's law, there is a relationship between average flow time, average flow rate, which is throughput, and average inventory. When we look at CSUN, when we go through the records at CSUN, we realize on average there are 36,000 students. That's average inventory. We may go through records and find it out on average each year 7,500 students graduate from CSUN. That's our throughput. And then we may go and ask each student, how long did it take you to get graduated? One student may say it took me 4 years. The other one may say it took me 5.5. We ask all those 7,500 students, add those times up and divide it by 7,500, and that would be the average flow time. However, according to the Little's law, there is one other way to find it out. On average, how long does it take a CSUN student to get graduated, using the throughput and the average inventory. The ultimate strategy of all for-profit enterprises is to have good financial performance. The essence of this strategy is to maximize net present value. In order to have good financial performance, we need to satisfy our customers. We cannot have good financial performance in the long run if we don't satisfy our customers. Customers define their expectation in a four-dimensional space of time, cost, quality, and variety. We promise them a customer value proposition to satisfy what they expect to have in this four-dimensional space. In order to be able to deliver that customer value proposition, we need to develop appropriate process competencies. Process competencies in the final analysis are translated into a four-dimensional space of time for time, cost for cost, quality for quality, and flexibility for variety. To improve financial performances, we need to satisfy our customers. To satisfy our customers, we need to propose them something which is consistent with the product attribute that they have defined in that four-dimensional space. In order to be able to deliver that customer value proposition, we need to develop process competencies in four-dimensional space of time, cost, quality, and flexibility. And the essence of these process competencies in the final analysis can be translated into the essence of process flow, which is the average inventory, throughput, and flow time. We are trying to prepare the stage for the Little's Law. And the Little's Law does not talk about this minute, this hour, next hour. It will talk about average per minute, average per hour, and so on. In a stable process, inflow rate is equal to outflow rate. What comes in goes out. 60 customers per hour come in, 60 per hour go out. In 1 hour, maybe 58 come in and 54 go out. In another hour, maybe 58 come in and 62 go out, because there are some inventory from the previous hour. However, we don't talk about hour 1, hour 2, hour 3. We talk about the average. Average inflow rate is equal to average outflow rate. We refer to average flow rate as throughput. Ideally, throughput, which we show it by R, should be equal to customer demand. We produce that much which is required by the market. Nothing less, nothing more. That is the ideal situation. Look at an airport security checkpoint. The book talks about Vancouver Airport. If you assume that the process is stable, then throughput is constant throughout the day. Suppose average flow rate is 600 passengers per hour. And because we assume it is uniformly distributed, so that would be 10 passengers per minute. The scanners at security checkpoint can handle 12 passengers per minute. Can we have 9 instead of 12? I don't think so, because if 10 passengers per minute come in, and we can handle 9 passengers per minute, after a while we have many passengers waiting in the line. You cannot say that after 8 hours we will stay for 2 more hours and handle the remaining passengers, because in that case for 8 hours you have 10 per minute, but for 2 hours you have 0 per minute. Your average flow rate would be 8 per minute for 10 hours, and here you have 9 passengers per minute for 10 hours. Then your capacity is more than the demand. You can handle it. Capacity cannot be less than demand. Can we have 20? Capacity and still have waiting line? So 10 passengers per minute come in. We have capacity of 20 passengers per minute. Can we still have waiting line? The answer, as we will see in the waiting line analysis, is yes. Why? Because there is variability. It is not the case that in each minute exactly 10 passengers come in. In some minutes there may be 0 passengers, in some minutes there may be 40 passengers. While capacity is much greater than the demand, still we may experience waiting line. We will discuss it later, but for the time being we are only concerned with averages. Average flow time, average inventory, which is the number of people waiting in the line, and average flow rate, which is throughput. average outflow capacity, which is process capacity, must be greater than average inflow rate, which is throughput, while the average inventory is not zero. Here is the Little's law. Flow units come into the system at rate of R per time unit, R units per hour, R units per day, R units per minute, and they leave the system at the same rate. Throughput is R units per unit of time, R units per hour, R units per minute, R units per day, R units per week. A flow unit at its entrance point into the system observes I flow units waiting there. While the flow unit is waiting, the waiting flow units leave the system one by one. When this flow unit reaches to the point to leave the system, it looks over its shoulder, and again there are I flow units waiting. It will take this flow unit T units of time to go through the process. During that T units of time, other flow units have come into the system at rate of R. How many flow units have been accumulated inside the system during that time period? I. In a time period of T, flow units have come in at rate of R, and I units have been accumulated. R times T is equal to I. An alternative way to explain the Little's law is units come into the system and leave the system at rate of R. On average, at any second, there are I units within the system. So I units are there. They are served at rate of R. How long does it take them to be served? T units of time. T times R is equal to I. Throughput times flow time is equal to inventory. In a security checkpoint in Vancouver Airport, on average there are 17.5 passengers waiting in the line. 17.5 on average means sometimes there are 18, sometimes there are 19, sometimes there are 17. When we add all these numbers and weighted average them, the average is 17.5. For example, if you have one person in a waiting line 50% of time, and there is no one in the waiting line for 50% of time, then on average we have 0.5% waiting in the line. The arrival rate at the security checkpoint is 600 passengers per hour. On average, 10 passengers per minute. On average, how long does it take a passenger to pass through the security checkpoint? R times T is equal to I. 10 passengers per minute times T is equal to 17.5. T is equal to 1.75. 1.75 what? Throughput is 10 passengers per minute. .75 minutes. In this example, we have a garage door production plant. On average, there are equivalent to 2,000 garage doors inside our plant. They are in different stages of production. On average, everything over there is equivalent to 2,000 completed garage doors. Our production rate is 1,000 garage doors per week. Total cost of production of each garage door is $3,300. Suppose we pay for raw material and everything when a flow unit enters into the system and collect what we have paid when the garage door leaves the system. Now I want to translate throughput and inventory into dollar and find it out on average. How long does it take from the time that I put $1 into the system until the time that I get that dollar back? What is the flow time of $1 inside my system? I have equivalent of 2,000 garage doors in inventory. Each one costs me $3,300. So on average, I have $6,600,000 in inventory. Each week, I produce 1,000 garage doors. Costs of goods sold is $3,300. Therefore, my throughput rate is $3,300,000 per week. I implement the Little's law. I is $6,600,000. R is $3,300,000 per week. Therefore, the average flow time of $1 is 2 weeks. Weeks because throughput is explained in terms of weeks. These are my last attempts to try to make the Little's law clear and also make it clear the difference between throughput and inventory. Suppose we have an insurance clerk. Every day 80 applications come on his desk, and because we are in a steady state, we are in a stable process, 80 will go out. On average, there are 20 applications waiting on his desk. What is the flow time? How long does it take an application to come here and go out? 80 is R. 20 is I. R times T is equal to I. R is 80. T we don't know. I is 20. T is 20 divided by 80, which is equal to 1/4 of a day, because 80 is per day. So T is 1/4 a day, or if a day is 8 hours, it is 2 hours. In an earlier example, I said let's assume CSUN has 36,000 students. And I said let's suppose each year we accept 7,500 new students. How long does it take for an average CSUN student to get graduate? Each year 7,500 come in and 7,500 go out. So R is equal to 7,500 per year. The number of students who are still a student at CSUN is 36,000. That is I. R 7,500 times T is equal to I 36,000. T is equal to 4.8 years. Based on this example, cash transactions in Europe is around 300 billion euros per year. 300 billion per year. Each person or each entity, when they take cash, they keep it for an average of 2 months. 2 months. How many coins do we need? This is R. This is T in terms of months. R and T must be of the same nature. 300 per year divided by 12, that would be 25 billion per month. R times T is equal to I. 25 per month multiplied by 2 months is equal to 50 billion, and that is equal to I, the volume of coins that we need. So here I had 300 per year. I could have translated 2 months into year. 2 months is 2 divided by 12, or 1/6 year. R times T is equal to I. 300 times 1/6, it is equal to 50, equal to I. So it doesn't matter if I translate time unit of R into T or T into R, but they both should be stated in terms of a unique time unit. Here Taco Bell serves 1500 customers in 15 hours. So that is 1500 divided by 15, that would be 100 per hour, and that is R. On average, there are 75 customers in the restaurant. I is 75. How long does an average customer spend at Taco Bell? R times T is equal to I. 100 times T is equal to 75. T is equal to 0.75 hour, or 45 minutes. And what is average customer turnover? Turnover is defined as R divided by I. R is 100 per hour, I is 75. Therefore, customer turnover per hour is 1.33. If you want a customer turnover per day, it is 1500 divided by 75, and that would be 20. Turnover means how many times do we replenish inventory. Here, in each hour, our seats are emptied and filled 1.33 times. In one day, 20 times. See if you can solve this problem. Stop the recording and solve the problem. R equal to 10,000 per year. The average processing time 3 weeks. T equal to 3 weeks. What is the average number of claims in process? What is I? 10,000 come in. They go into the process and 10,000 go out. But on average, there are I units over there. And it takes a flow unit to go from here to there 3 weeks. I should state R and T in the same time unit. R is 10,000 per year and year is 50 weeks. 10,000 divided by 50 is equal to 200. 200 per week. Here I have 200 per week, and here I have 200 per R times T is equal to I. 200 times 3 is equal to I. On average, 600 claims are waiting there. Solve this problem quickly. R equal to 5,000 per week. I is equal to 2,500. R times T is equal to I. 5,000 times T is equal to 2,500. T is equal to 0.5 week. $300 million sales. So we send $300 million statement to our customers. This is our account receivable. We send statement to our customers. They send cash to us. On average, we have 45 million account receivable. Sales is 300 million. We send 300 million statements and we collect $300 million. How long does it take from the time that we send a statement until the time that we get the cash? R times T is equal to I. 300 million per year times T is equal to 45. Therefore, T is equal to 45 divided by 300. .15 year or if I multiply it by 12, 1.8 month. A steel plant, process 400 raw material, 200 labor and capital cost, 600 cost of goods sold. 600 comes in, $600 goes out. Average inventory 100. What is the flow time for $1? From the start of the process until that dollar leave the process. Flow unit is a dollar cost. Process is still manufacturing. Average inventory is 100. Throughput is 600. Flow time, R times T, equal to I, 600, T equal to 100, T is equal to 1/6. And 1/6 of a year is 2 months. In this example, a manager states that their inventory turns 3 times a year. Inventory turn is defined as throughput divided by average inventory. If throughput is per year, inventory turn is per year. If throughput is per month, inventory turn is per month. If throughput is per day, inventory turn is per day. But look at T. R times T is equal to I. Therefore, T is equal to I divided by R. I divided by R divided by I. Inventory turn is equal to 1/T. For example, if T is 3 months, inventory turn is 1/3 per month. And if I want to change it to year, that would be 1/3 times 12, that would be 4. The takeaway of this discussion is inventory turn is equal to R divided by I, which is equal to 1 divided by T. R divided by I is equal to 3, which is equal to 1/T, and therefore 3T is equal to 1, and therefore T is equal to 1/3, and 1/3 year is 4. Months. At the same time, she claims that whatever their company gets, it is processed in 6 weeks. 6 weeks is about 1.5 months, and this one says it is about 4 months. Contradiction. These two statements are not consistent. Out of 3 operational measures of performance, inventory, throughput, and flow time, we need only 2 of them. As soon as we have 2 of them, we can compute the third one. Do we collect data regarding R and T, or R and I, or I and T? And if I have R and T, I can compute I. If I have R and I can compute T. If I have I and T, I can compute R. Collecting data regarding which pair is cheaper? If I want to collect data regarding T, then for each patient who comes to the physician office, we should put a tag on him, when did you come in? And I should put a tag on him when he leaves. Then I subtract those 2 numbers and find the time that flow unit has spent in the system. And then I should compute it for all flow units and average it, and that would be the flow time. For each CSUN graduate, I should go and find it out when he or she came into CSUN and when he or she got graduated. Subtract those 2 numbers from each other, average it for all CSUN graduates, and that is the flow time. An expensive job. I don't want to do that. What about R? Is it expensive to collect data regarding R? No. All companies already have information regarding R. Every hour, every day, every week, they write down how many units they have produced. So I really don't need any additional time and effort and budget to collect data regarding R. What about I? It is not as cheap as R, but at the same time it is not as expensive as T. Companies have inventory system. When I look into the system, I can find it out how much inventory is there. All of the companies, they also have 1 or 2 or 3 times physical inventory check. They go and count the inventory they have to find it out, the difference between physical inventory and what they do have in computer. That data is also there. Out of 3 operational measures of performance, I collect data regarding T and I and use that to compute T. I ask CSUN how many students are there? 36,000. On average, how many students are graduated per year? 7,500. T is equal to 36,000 divided by 7,500, as we discussed it earlier. 4.8 years. So we have R times T is equal to I. We always want to reduce T. That is our main objective. One way to reduce T for a given R is to reduce I. Another way to reduce T for a given I is to increase R.